A 50 kilogram copper block, initially at 140 degrees C, is dropped into an insulated tank that contains 90 liters of water at 10 degrees C. I'm going to write down the givens. Mass of copper is given 50 kilogram. Initial temperature of copper is given 140 degrees C. Volume of water tank is given 90 liters, and I can divide it by 1000 to convert it to meter cubed, and the initial temperature of water is given as well, 10 degrees C. Determine the final equilibrium temperature and the total entropy change for this process. I'm going to take the entire tank, both water and copper, as the system. And this is a closed system because no mass transfers the boundary of the system during this process. So this is going to be our closed system. And I'm going to write down the first law of thermodynamics to solve this problem. Delta E of system equals E in minus E out. And I'm going to write down my assumptions to simplify this equation. Problem says that this is an insulated tank, so there is no heat transfer to or from the system. I'm going to assume that this is a rigid tank because there is no change in the volume of the tank or boundary work equals 0. I'm going to assume there is no change in kinetic energy and potential energy. And this is a closed system. So there is going to be no mass transfer to or from the system. So first law will become left-hand side, delta E system equals delta U equals right-hand side E in, which is 0, minus E out, which is 0. And the system consists of two substances, copper and water. So delta U of copper plus delta U of water equals 0. And from chapter 4, we know that delta U for solids and liquids can be determined using this equation, mass times specific heat times delta T. So I'm going to use this equation, mc T2 minus T1 for copper plus mc T2 minus T1 for water equals 0. And let's see what is given in the problem statement. Mass of copper is given 50 kilogram. Specific heat of copper that has to be read at average temperature. I'm going to assume that the average temperature is 25 degrees C, 0.386 kilojoule per kilogram Kelvin from table A3b at average temperature, which is 25 degrees. T2 is not given in the problem statement. We are interested in the equilibrium temperature. T1 for copper is 140 degrees C. Mass of water can be determined using this equation. Mass equals to density times volume. And from table A3a, I can read the density. We already assumed that the average temperature is 25 degrees C, so the density is 997 kilogram per meter cubed, and the volume is given in the problem statement, 0.09 meter cubed. Specific heat of water from table A3a at 25 degrees C is 4.18 kilojoule per kilogram Kelvin. Again, table A3a at 25 degrees C, T2 is not known, and T1 for water is given 10 degrees C. So one equation, one unknown, we can solve for temperature. It's going to be 16.36 degrees C or 289.36 Kelvin. Next step, we're supposed to solve for entropy change. Entropy change of total system equals entropy change of copper plus entropy change of water. And we're going to use this equation for change of entropy per mass in solids and liquids. Integral of C dt divided by temperature or specific heat at average temperature natural log of T2 divided by T1. So delta S total equals MC natural log of T2 divided by T1 of copper plus MC natural log of T2 divided by T1 of water. So once again, mass of copper is given in the problem statement, 50 kilogram. Specific heat has to be read at average temperature. For copper, the average temperature is 140 degrees C plus 16.36 degrees C divided by 2, which is 78.2 degrees C. And from table A3b, we can read for specific heat 0.3909 kilojoule per kilogram Kelvin. T2, we just solved for it, 289.36 Kelvin. T1 is given in the problem statement. It is 140 degrees C or 413 Kelvin. Mass of water can be determined from this equation. One more time, mass equals to density times volume. Density has to be read at average temperature, which is 10 degrees C plus 16.36 degrees C divided by 2 or 13.2 degrees C. So from table A3A, this is going to be 998 kilogram per meter cubed times volume, which is 0.09 meter cubed. Specific volume has to be read at average temperature 13.2 degrees C, which is 4.2 kilojoule per kilogram Kelvin. From table A3A, T2 is known, 289.36 Kelvin, and T1 is 10 degrees C or 283 Kelvin. So all the terms are known. We can solve for delta S total. It is going to be 1.4305 kilojoule per Kelvin.